Alright, welcome to Harry Potter and the Equation of Path. So essentially we're just figuring out really general forms for the for equations to give you the path of a projectile without having to rely on knowing specific times. So let's say we have fired from the origin. So we've got a thing. So when t equals 0, x equals 0 and y equals 0. So r as a function of t is xi plus y. J, so r as a function of t is, 0i plus 0j. The velocities, so x dot and y dot, we're going to zoom in. And let's say we took off with initial velocity v meters per second at angle theta up from horizontal. So this is theta and this is big V. So this will be x dot and this will be y dot. So x dot at 0, because this is only at 0, is v cos theta, and y dot at 0 is v sine theta. But we also know from that x dot dot is always going to be 0, and y dot dot is always, as a function of t, is always going to be 0. Y dot dot as a function of t is going to be negative g, yeah? So if we were to integrate that, if we wanted x dot as a function of t, well, that's the integral of this. So that just comes out as a constant term. So this is very much like what we did a lot last exercise. This is going to be I want to give some more working out. Plus C2. Okay. Which means x dot 0 is v cos theta equals C1. Y dot 0 is minus g times 0 plus C2 comes out as, I should have done this the other way around for consistency, v sine theta, which comes out as minus g times 0 plus C2. So C1 is v cos theta, C2 is v sine theta. So we have the general equations, x dot t, so for the horizontal velocity, v cos theta, for the vertical velocity, negative gt plus v sine theta. Yep, okay. Okay, and now I'm going to integrate again. So we're integrating v cos theta. So it's going to be v cos theta times t plus c3. Another way to write this is vt cos theta. Same with y. We're integrating y dot. Oh, I should have put brackets t, whatever. So this one comes out as we're integrating negative gt plus v sine theta with respect to t. So it's negative gt squared on 2 plus vt sine theta plus c4. Okay, we know x at 0 is 0, so it's v times 0 cos theta plus c3, and it's 0 because we're taking off from the origin, so c3 is 0. We know y at time 0 is negative g times 0 squared over 2 plus v times 0 sine theta plus c4. We know it equals 0, so c4 is 0. So x at t, just means we don't have the constant terms. Vt cos theta, y at t equals negative gt squared over 2 plus vt sine theta. We know v itself, x squared plus y, v squared equals x squared plus y squared, yeah? Because wait, can I do that? Don't need to. Okay, so if I choose this one to rearrange, mostly because it's going to be easier than the other one, I can get an expression for t. So I'm going to say t equals x as a function of t over v cos theta. If I then sub that into y, and if I get rid of these, x as a function of t, y as a function of t, if I sub that into y for t, then I've got negative g on 2 times x on v cos theta squared plus v times x on v cos theta times sine theta. So I get negative gx squared over 2v squared cos squared theta plus, the v's cancel out, x on cos theta times sine theta. Well, that's the same as sine on cos, so that becomes tan. And that cos being on the bottom means I can rewrite this one as negative gx squared on 2v squared times sec squared theta, which is just going to be a bit easier to integrate and yeah, you know what I mean. We also knew that sec squared theta is 1 plus tan squared theta. So we get y equals negative gx squared over 2v squared times 1 plus tan squared theta plus x tan theta. And that's what we're after. Apparently you're supposed to be able to derive this one. I'm assuming they'd talk you through the steps. yeah, this one's also very useful.